Today, what I want to talk about is what's called the average rate of change of a function, and it's always going to be on an interval. Okay, so this is some function. I'm going to call it y equals f of x, and that's this curve right here. Okay, and there's 2 points on it, and this point right here, I'm going to label the x coordinate. I'm going to call it a, and then this coordinate right here, I'm going to call b. Okay, and since this is the function, this point right here would be a comma f of a. And this point right here would be, since that x coordinate is b and we're putting it into f, this would be b comma f of b. Okay, and if we draw a line between these 2 points, we can determine a slope between 2 points. Okay, so I'm going to do that. So I'm going to draw this line, and there's a name for this line. Okay, and this line is called a secant line, and it secant and then line. Okay, and so we can find the slope. So the secant slope, we would call it the secant slope, is really just from math 1. And I need to slide it. Hold on, I'm going to zoom out a little bit. Okay, slide it up a little bit. Okay, so secant slope is the change in y over the change in x. Okay, so in this case, it would be f of b, because that's the one on the right. Okay, f of b minus f of a all over the change in x, which it went from a to b, so that's a difference of b minus a. Okay, so that's called the secant slope. All right, and this is also called the average rate of change. So it's the y coordinate is changing, and there's a rate at which it's changing. Okay, and the average of those rates is called the average rate of change. Okay, so that we also say average rate of change. I'm going to slide it up a little bit more. Average rate of change. And I need to zoom out a little bit more. Okay, there we go. Sorry about that. Change on, and we have to say an interval, so this interval is going to be a closed interval, a to b, all right? And this would be equal to the change in y over the change in x, which would be f of b minus f of a all over b minus a. All right. They also call this AROC for the first letters here, AROC. So they sometimes call it AROC. AROC, average rate of change. Okay. All right. So you did this in algebra and in math 1, math 2, math 3. Okay. But what happens is, and this is what we need limits for, okay? What happens as we bring this point and we move it along the curve, okay? And I'm going to show you a video in a little bit on this, okay? And I move this point along the curve, and what happens is this slope that's between 2 points becomes the slope at 1 point, okay? And it just barely touches it right here, okay? And so I'm going to draw another line that's just barely, I'm trying to touch it, just barely, just touch it, okay? Right about here, okay? If I brought this point in, this would be right here. This would be an example of a tangent line. So it's just barely touching it, okay? It's touching the curve at 1 point only, okay? And this is called the tangent line. And this is going to be really important in calculus, this tangent line. This is actually what we're going to be doing, really spending the whole first semester figuring out this tangent line. Basically, that's it. And it tells us stuff about the function, okay? So I'm going to zoom out one more time, okay? And slide this up a little bit, okay? And so what the tangent slope is it's called the instantaneous rate of change. Okay, and sometimes people call this IROC. All right. You'll also, when somebody says, so they'll say, find the instantaneous rate of change. What they mean is the tangent slope. You'll also hear them say rate of change. And I should say this, your speedometer on your car, it tells you the your instantaneous speed. So that is an instantaneous rate of change, okay? It's the rate of how two things are changing, okay? This is gonna be really important, okay? If we get this point and we get really close to this 1 point, right, then that would be a pretty good estimate of the tangent slope, okay? So we can estimate, and that's what we're actually gonna do today. We can estimate using a secant line with 2 points, because we still need 2 points, okay? 2 points. Very close, very close together. That was supposed to be one word. Okay, hold on. A little white out there. Okay, together. All right. So I'm going to take you and I'm going to show you what I mean by this, what this looks like for a secant line to become a tangent line, okay? And I'm going to show you that with a little animation. So in this animation, what I want to show you is that I'm going to create a second point on this curve. We call this curve the function f. So I'm going to create this point Q. And then what I'm going to do is I'm going to connect them, and that's a secant slope, okay? And the slope right now is 1.384. So that would be the average rate of change between whatever the x value is for point P and the x value is for point Q. All right, and what I'm going to show you is that what we're going to do is we're going to estimate the instantaneous rate of change with secant lines, and then eventually this point's going to be right on top of P. So what happens is we move Q, and there's ways we do this with mathematics. I'm going to show you that tomorrow, okay? So we're going to let H, I'm going to make this, I'm going to stop that. Okay, so that would be we're a little bit closer to P, so that's a better estimate than we were just a second ago. That one's a little bit better. And what I say better is it's a better estimate for the tangent line, the slope of the tangent line at point P, which is also the instantaneous rate of change at point P. So I'm going to get a little bit closer. That wouldn't be even better. That would be even better. Okay, and you see how it's just going to be touching it in just a second. It's just going to touch it right. Well, we just missed it, right? So I'm going to do it one more time. And then I'm going to create the tangent segment. And it's going to, that black line right there would be the tangent. So that what that means is that line right there is only touching the curve at one point right there, right where it flashed on us. Right there, okay? So there's what I want you to understand right now, okay, is that there's two different types of slope. There's average rate of change slope, that's between 2 points. That's what you've learned over the course of your high school mathematics. And then there's also this new thing called the instantaneous rate of change, which is slope at a point, all right? And that's really all I want you to understand right now, okay? And that's it. So we'll go back. So what I want to talk about this is how we use this average rate of change in physics, okay? So in physics, we talked about distance, and we called it S a lot of times, all right? I don't know if Mr. Jet always called it S or not, but that's all right, okay? It's the function S. So displacement, or the change in distance, would be S of T sub 2 minus S of T sub 1, okay? And that's called it's also called the change in position. So how much you moved? Well, I shouldn't, it's more than just that, okay? Units for something like this would be meters, yards, it's be some distance unit, okay, some length unit. There is no slope associated with displacement, okay? Then we move on to velocity, okay? And velocity becomes, it's the change in position over the change in time. And when we talk about velocity in this sense, it's the average rate, it's the average velocity, okay? So we'd have some units like this, meters per second. We could also have miles per hour, okay? And it's, since this is S, the slope for this, if we looked at the velocity function, the slope of that velocity would be the delta S over delta T. Okay, then we move on and there's acceleration. Well, acceleration is tells you how the velocity is changing. And I should go back. Velocity is telling us how the distance is changing, how fast it's changing. Okay, acceleration tells us how the velocity is changing. So this would be the change in velocity over the change in time. Okay, so the best units, but it's not the best way in mathematics to write it, but the best way to explain it is, since these units for change in time would be meters per second, this would be meters per second over second. But that's a complex fraction, right? And that's a little more cumbersome. So what we do is we simplify that complex fraction, and this actually becomes meters per second squared. When we say meters per second squared, that's a little harder to understand. What we mean by that is really this, meters per second, okay? And so we would have for slope, delta V over delta T, the change in velocity or the change in time, change in position or the change in time. So when we look at a velocity graph, the slope of a velocity graph would be the change in, well, it'd be delta S over delta T. I'm sorry, I said that wrong. If you look at a position graph and you look at the slope, that would be the change in position over the change in time. If you look at a velocity graph, the slope would be the acceleration, delta V over delta T. And we're going to get more into this later on, okay? Really what I want you to be able to do is this example right here that we're going to do next, okay? And that is find the average rate of change of f of x for, which equals x cubed minus x over this interval. So I have to give you an interval to do average rate of change, okay? So we could write delta y over delta x. That's the average rate of change. And this would equal f of 3. I always do the point on the right. You don't have to, but that's normally how we write it. And it's going to make more sense when we go into calculus to put it on the right, okay? More people do it that way. So f of 3 minus f of 1 over 3 minus 1. Now, for reasons that you don't know yet, I would actually, don't do this in your head, okay? Learn to write it out like this, okay? So we're going to use a bracket, and this first bracket is us putting the 3 into the function. So that'd be 3 cubed minus 3, and then minus, and then 1 cubed minus 1. I realize a lot of you are good at math, and you can do this in your head. That's not the purpose of this, okay? Just know that's not it, all right? So then 3 cubed, now we can do the math. Okay, so 3 cubed is 27, and then 27 minus the 3 would give you the 24, minus, and this would be 1 cubed, which is 1, minus 1, so that'd be 0, over, and then 3 minus 1. And so this would give you 24 over 3, which, I'm not 24 over 3, 24 over 2, which would give you a slope of 12. So the average rate of change for this function between 1 and 3 is 12. So we look at this next problem, okay, and it's a growing Drosophila in the laboratory. Drosophila are fruit flies, okay? And this used to be a lab you did in AP Bio, okay? I did it at UC Santa Barbara, and you just grow fruit flies, and you look at the rate of change and you'd look at the genetics and how it's changing and all that. But anyway, that's besides the point on this problem, okay? This is just telling you that they're reproducing, okay? On day 23, there's 150 flies, okay? 24th day, there's 168. 27th day, there's 220, and so on, okay? And so we want to use the points P, which is 23,150, and that's this one right here, and Q, it's this last one, this Q1 right here, okay? So 45,340, so that's on the 45th day, there's 340 flies, and we want to compute the average rate of change and the slope of the secant line, PQ, all right? So if we want to find the slope of the secant line PQ, that's going to give us between days 23 and days 45 the average rate of change, because the number of flies is changing. It's not staying the same. So there's a change in that. So that's rate of change. Okay. So for this, we're going to do, I'm going to connect them first. I'm going to draw this. So we're finding the slope between this point P and this Q1. So this is going to be a problem similar to what you're going to have on the homework. Okay, so what I'm doing is I'm finding the slope between those 2 points. So it's this slope. I mean, it's not the curve, right? We're not, okay? And it's a little bit different, but what this is if we took all the slopes in here and we averaged them, all right, then what we would have is this number that we're going to get, okay? So change in Y over the change in X is equal to, and I'm going to do the one on the right, so that's 340, so 340. And then minus the 150, because those are the outputs or Y values, and then 45 minus 23. I think we do the one on the right first, because then when we subtract on the bottom, the denominator is always going to be positive, okay? I think that's probably why we do it. So this comes out to be 190 over 22. And then we put that into our calculator, and we get a unit rate, which is 8.636, and this would be flies per day. So on average, between days 23 and days 45, on average, the fruit flies are increasing by almost, if we round, 9 flies a day, okay? All right, so if you look right here, between day 40 and day 45, it only increased 10 flies, right? But over here between days 23 and 24, it increased 100, or not 100, it increased 18, okay? So it is changing, because this is 10, this is 18, right? But on average, this is what it would be between days 23 and days 45, okay? So we would write this up, and we would say something like this: between days 23 and 45, on average, so the slope is describing the output here, which is this. It's describing how this is changing, okay? On average, this, which is number of flies or number of fruit flies, and we'd say is, and since the slope is positive, we say is increasing. .636 flies per day. Okay, and that's how you do that example too. All right, so now we want to actually, okay, so what is it exactly on day 23? Well, I'm going to tell you right now, we can't do it. Okay, we don't have the knowledge to do it. But what we can do is estimate it, and that's what I want to do today. Okay, we can't actually find it yet. We will be able to. That's what calculus does for us. Okay, but right now what we're going to do is we're going to draw some lines. Okay, And let me get my red pen. All right, so what we're gonna do is I'm gonna draw some lines. So we already did the secant line. So what we want is right here, we want that slope that just touches point P right at one point, right in here. But the only way to get that is to start working our way. And I'm gonna do this slope right here between P and Q2. And then I'm gonna do P and Q3. And then I'm gonna do P and Q4. P and Q5, and then P and Q6. Okay, and that last one, P and Q6, is the closest we could get to point P. And Q6 is the 24th day, right? Okay. All right, so we can do this. I'm gonna slide it up a little bit. We can do this. We're gonna find the slope. We're gonna estimate it by finding the slope of P and this Q6, Q sub 6. All right, so that would be the change in Y over the change in X, which is, okay, so between these 2 points, it's 168 to 150. So 168 minus 150 over 24 minus 23. And that'd be 18 over 1, which is 18 flies per day. Okay, so what's the growth rate on day 23? On day 23, comma, the flies, the number of flies, I should say number of flies, the number of flies is increasing 18 flies per day. And a lot of times, okay, so this is the things that they're going to ask you if we have to take the AP exam online. They don't ask you to calculate stuff because they know you can Google that. All right, they're going to ask you the interpretation, and you have to learn how to write this up. So this is, and we're going to do more practice on this, but this is the write up on this. Like, this is describing how it's changing. Okay, it's very academic language, but you got to learn how to write that way. Okay. All right, you guys, let's go to the next one. So this was a question from the 2014 exam, okay, and you were able to use a calculator because we're going to need to get some Y values out of a complicated function, okay? So grass clippings are placed in a bin where they decompose. For 0 less than or equal to t less than or equal to 30, the amount of grass clippings remaining in the bin is modeled by A of t. Okay, so this A of t, and this is the start of preparing for the AP exam, okay? What is this A of t? It's the amount, it's how much grass clippings are not being put into the bin, but that are remaining in the bin, okay, that are staying in the bin, okay? Where A of t is measured in pounds and t is measured in days, okay? So find the average rate of change of A of t over the interval 0 less than or equal to t less than or equal to 30. And this A of t is an exponential function, okay? So it's 6.687 times 0.931 raised to the t. And I'm going to grab a graphing calculator, okay? I'm going to work this out, but there is a write-up. It's not just about getting the right answer, the correct write-up. So we need to have the indicate units of measurement. And I would also say show your work, okay? Show the work that leads to your answer. Okay, so we're going to go between 0 and 30, all right? So that would be A of 30. We can write like this. I would use the function notation, A of 30 minus A of 0, because we're trying to find it between 0 and 30, over 30 minus 0. All right? So we're going to go to our graphing calculator now, okay? And we'll put that into our graphing calculator, and then we'll have it, okay? So what I want to do on this is I want to go to my graphing calculator. I want to press y equals, and then I want to type in the function A of t, which is 6.0 687, and then parenthesis times, and then 0.931, and then close the parenthesis and raise that to the t power, which will do x, okay? All right, so we'll go back. So now we can put values into this function and get them out. So this is how you do it on the graphing calculator. All right, so we're going to go to the home screen. So we want to quit. All right, and then we want to create a fraction, and then we want to put in y1 of 30. So that'd be alpha trace, and then number 1 here, and we put it in as a function. So y1 of 30. And then minus y1 of 0. So alpha trace again, y1 of 0. We need the parentheses here, because when you have y1 and it has the parentheses, it knows you're talking about that as a function, okay? And then 30 minus 0. And this would be showing your work, okay? And then it equal this, all right? All right, so that's our average rate of change for A of t, and we're using it to estimate, or well, actually, I'm taking that back. We're just finding the average rate of change for this. So from our graphing calculator, we see, and we're going to round to 3 decimal places, okay? This turns out to be negative 0.197 pounds per day. Okay, so the write-up on this, okay, and we need to learn to write this up, between 0 and 30 days, because the time is measured in days, comma, on average, the amount, we got to take the time to write this correctly. If you say amount of grass clippings, you're wrong. If you say amount of grass clippings, you're wrong. It's the amount of grass clippings remaining in the bin, okay? So on average, the amount of grass clippings remaining in the bin is decreasing. Okay, so how do I know it's decreasing? Because my slope here is turning out to be negative, okay? Now that takes care of the negative, so I don't need to use the number negative 0.197. We're just, that's decreasing is the negative, okay? And so then we write 0.197 pounds per day. Okay? And guys, that's average rate of change. It really is just slope, okay? Slope between 2 points is average rate of change. All right? That's it for today, guys.